Yeah, welcome to the new module, that is module number 9, that is on introduction to automatic test pattern generation and ATPG algebra. So, in the last module, that is module number 8, we have discussed two basic stuff, that is when you have to generate or have to test a stacked fault. So, what we do basically, we first have to find out a pattern which can detect the stacked fault, that is you have to find out a pattern which can differentiate that the circuit is either having a stacked fault or the circuit is normal. Like for an AND gate, if you want to test a stacked 0 fault at the output, you have to apply 1 1 at the input. So, if the circuit is normal, you will get 1 at the output, and otherwise if there is a fault, you will get 0 at the output. So, we have seen basically two procedures. One is that is the random test pattern generation, in which we apply one test pattern and then find out how many faults can be detected by that. And then we have found out that there can be another procedure which is called the sensitize, propagate and justify approach. In sensitize, propagate and justify approach, what we do? We take a fault, then drive it to a reverse value, then we try to drive it to the output at some primary output, drive the effect to the primary output, and then we want to justify that for doing this sensitization and propagation, whatever is required at the primary inputs, as those values we try to apply and verify that we can do that. Now, we have found out that what you call the random test pattern generation by ATPG is algorithmically simple or computationally simple than sensitize, propagate and justify approach, because in the random test pattern generation based approach, you apply one pattern and then find out more than one number of faults that can detect it in a general case. But in case of sensitize, propagate and justify approach, you take one fault and find out a pattern, take another fault and find out a pattern. So, it may happen that two faults which can be detected by the same pattern, you have to lead to two different iterations of the algorithm. But all faults cannot be detected by fault test patterns cannot be generated for all faults in a circuit, because some faults are easy to test and some are difficult to test. For easy to test faults, we can go for the random test pattern generation approach, but for the difficult ones, we will find out that the number of random test patterns applied and the trials are much more in number. That is, you apply a random pattern, do not detect a fault, then you apply another random pattern, you keep on doing it, and this iteration has to go for a large number of times for the difficult to test fault. So, for that, whenever we find that the random test pattern generation performance is degrading, that is for a given new random pattern, not much new faults are being detected by that. So, what we do that? We go for the sensitize, propagate and justify approach. Also, we have seen one algorithm which is called the SQAP, that was in the last lecture, that how can you differentiate or how can you demarcate in a heuristical manner, that is maybe an approximate way, which are the easy faults and which are the difficult to test faults. For easy faults, we directly go for the random pattern generation algorithm, and for the difficult ones we go for a sensitize, propagate and justify approach. So, in this module, that is module number 9, so, in module number 9, what we are going to do? We are going to see we will deal with automatic test pattern generation algorithm, that is we will deal in details or in a formal way how do you go for sensitize, propagate and justify approach for test pattern generation. Before that, in this lecture we want to see that we want to see the basic introduction, and also we have to see for some ATPG algebra. That is, if we are using what you call this sensitize, propagate and justify approach, then this Boolean algebra which is 0 and 1 may not suffice. That is, we require a higher degree algebra, that is higher means we will see that what I mean by that. So, higher order algebra may be required, in which case we will have 0, 1 and some other symbols which can help in sensitize, propagate and justify approach. So, already told you that some faults are easy to test and some are difficult to test. So, algorithm like SQAP actually generates this bin for you, which is easy to fault and difficult to test. So, for sensitize, propagate and justify approach, okay, for easy faults we go for random patterns, and for the difficult we go for sensitize, propagate and justify approach. So, in this lecture we will see the basics of ATPG and ATPG algebras, and in the next lecture we will see the D algorithm, which is the basic algorithm for sensitize, propagate and justify based approach for pattern generation. So, now we will go for ATPG and ATPG algebras, we will see why it is required. So, basically random test pattern generation is also can be called as automatic test pattern generation, that is ATPG. But generally, if you look at the random test pattern generation based algorithm, then we do not generally generate a test pattern. What we do, I mean we generate a test pattern, but very formally speaking we do not do that. So, what we do, we apply a pattern and find out how many faults are detected by this. So, this is called random test pattern generation, random test pattern based testing kind of a thing. Okay, but truly speaking, what do you mean by test pattern generation? Test pattern generation or automatic test pattern generation should be given a fault, then find out any pattern pattern that can detect it, or all patterns or more than one pattern that can detect it. Actually in sensitize, propagate and justify approach we do exactly this way. We have a fault and then find out a pattern for doing it. So we can say quote unquote that this is exactly automatic trace pattern generation, and in some places in the literature we may not call random trace pattern generation as automatic trace pattern generation, because they call it that we apply a pattern and then find out which faults are detected. But if you want to speak broadly, then both of them, that is sensitize, propagate and justify based approach and random trace pattern generation approach, both of them are automatic trace pattern generation for the for detecting stacked faults or bridging fault, any fault model you can take. Okay, but if you go by the literature, that we call ATPG for mainly sensitize, propagate and justify approach. Okay. So, this is what will be terminology we will be using. So, till now exactly before we come to in details of ATPG, LTPG, algebras and ATPG by sensitize, propagate and justify. So, let me just give you a quick view that the random trace pattern generation and what you call the sensitize, propagate and justify are Boolean logic based test pattern generation. That is, we do mathematically, we have a circuit. In fact, initially when you are going for automatic test pattern generation or random test pattern generation, we do not have the circuit. So, what we do is that we have the soft copy of the circuit, or we have a program for the circuit, or we have a event driven model of the circuit, and then we try to apply algorithms to find out which test patterns can detect which fault. So, this is actually called Boolean logic manipulation based test pattern generation. But there can be some other physical or layout based or some other technique based stuff which can also detect fault. One very important part is actually called the thermal imaging. So, which is not a pure Boolean manipulation based stuff, and in this case what we do, we require this circuit. So, in this case what happens, we take a circuit, and then when the circuit has been fabricated, then we take a thermal image. Actually we open up the fabrication, I mean mostly the chips we have seen the black color or the with black color cover and all those things which are layout in your computer motherboard or which is in your mobile motherboard or some places are actually package chip. So, if you do not have the package chip, then we have the raw fabricated IC, then we put it in the power, apply patterns, and then we take a camera and we take the thermal image. That is based on the flow of currents and voltages in the circuit, depending on the flow of current and the application of the voltages at different parts of the circuit, we get different temperatures. So, this temperature profile is recorded by a thermal imaging camera, and then we analyze. Say for example, where do we know that, say there is a line that is going, and say this line it is VDD, somewhere it is connected, and then this line is stuck at 0. Then what happens basically, this line is connected to ground. So, there is a VDD that is the 5 volts or the 3.3 volts or whatever is your one logic, one voltage, and it is stuck at 0 means it is connected to ground. So, there is a short from a voltage VDD source to ground source. So, a lot of current, this current flow will be very high, and there will be a huge temperature in around this region. So, then your thermal imaging will show some red spots in the some places of this faults. So, then you can easily point out that regions wherever there is high amount of voltages, where there is low temperature, where there is high temperature, based on different temperature profiling, you can find out which areas there may be faults and which area there may not be any fault. Like for example, as I told you, if there is a short from VDD to ground, then there will be a lot of current flow, and then there will be, it will be a very red hot spot will be there, and your thermal imaging camera can detect there is a very hot spot, and there may be some defect in this area. So, you can pinpoint those faults. So, I mean that is actually saying the absorption is higher when there is a stuck at 0 fault and there is a stuck at 1 fault, which you have seen. Okay, because I mean fault areas generally do have what you call maybe there is a stuck at 1 fault over at this point, and for some reason you apply a 0 volt at this line. So, then it will also have a source from stuck at 1 to ground. Okay. So, you are applying a 0 volt means it is connected to ground kind of a stuff, and the line is net is stuck at 1 means it is connected to VDD. So, lot of current flow will be there, and there will be a hot spot. So, all the regions for the faults will generally have some hot spot kind of a stuff. So, if you have too many hot spots, then you can find out that those regions may not be normal. So, this way also you can detect the faults. So, you can say that this is one totally different arena of fault testing, I mean or test pattern generation, which we have not yet discussed till now, and in fact we will not be also dealing with this in details, because this requires lot of information about fabrication, physical phenomena and all this, which is out of the scope of this scope of the course we are dealing with. So, for that it is basically covered in physical device fabrication and all those things, but still to give you the idea that always test pattern generation may not be based on logic manipulation, we have just quoted the example of thermal imaging. So, what is the advantage of thermal imaging? Thermal imaging is that you can directly have a dye, then you have a camera, then you can directly image out the thermal profile. So, you need not have to think about how currents are propagated to the primary outputs, how you can sensitize, because in case of a dye chip, you can chip based on package chip testing. So, you can only check the primary input and the outputs, control the primary inputs and check the primary outputs, but you do not have any control over the intermediary lines, because neither we can observe neither we can control. If we have to do that, we have to put additional circuit. But in case of thermal imaging, so there is some input patterns you give, and whatever temperature profile you can directly observe with the camera. So, you need not worry about or think about how I can generate a test pattern, how I can propagate it to the output, those problems are not there. But what is the disadvantage? Again, the disadvantage is the time required, or actually the expenses, the equipments required for them are very expensive. Thermal imaging, then you have to take the image, go for image processing and find out which is the hot spot. That actually takes more time for testing, and in fact the equipments are very expensive. So, again there is a trade off whether you have to go for logical testing or thermal imaging based testing. So, there is a trade off, and again sometimes we go for thermal imaging and sometimes we go for logic manipulation. But generally speaking, for the first initial few rounds of silicon fabrication, that when you are fabricating this chip for the first few rounds, then there may be lot of defects based on manufacturing, based on design problems. So, what we can do is that we can go for thermal imaging or exhaustive type of test. But once you are in the flow, that more or less the chip yield is coming to be fine, there is no more design errors which is manipulating to hardware errors and all. So, once things are more or less stabilized, then you can go for basically in the when you are going for this mass scale production, we generally go for logic manipulation based automatic test pattern generation. And also for this course, this thermal imaging or this physical type of testing is out of scope of the course. So, we will again go back to our logical manipulation based testing. So, let us see why we require a higher order, what you can order which is other than Boolean algebra. Why do we require some other algebra for automatic test pattern generation? So, we know that Boolean algebra comprises zeros and ones, that is very well known. So, what we say for example, if you have an AND gate, so input 1 I1 is 1 and I2 is 1. So, to detect a stacked one fault at the output, so it is very simple, we write 1 1 and in the output we say that in normal case it is 1, fault case it is 0. But the 0 1 slash what we are writing over here is not a very good way or formal way of writing. We require another symbol for this, because we have symbol for 0, we have symbol for 1. 0 means it is ground and 1 means it is logic high and 0 means logic low. This 1 0, what is this? It means that in normal case the circuit is 1 and the fault case circuit is 0. So, but this is actually not a very formal way of representing Boolean algebra, because we require some operation, like say for example we say 1 and 0 is equal to 0, 1 or 1 is equal to 1. So, we actually represent one symbol and here is one symbol, where zeros and ones are symbol. Generally in algebra we do not use something like 1 slash 0 or 1 slash 0. Then in the 1 slash 0, 1 slash 0 basically is equal to 1 slash 0 only, because 1 1 and 0 0, if you are it is 1 and a 0, but generally this is not a very formal way of representing. So, we require some specialized symbols to represent this fact, that is 0 1. Similarly, if it is an OR gate, it is another AND gate, we apply 0 0, then if we can easily detect a stacked one fault over here, because in normal case the answer is 0, fault case the answer is 1. But to represent these two stuff, we require some special symbols. So, that is the motivation of requirement of some kind of extra symbols or a higher order algebra for ATPG generation. So, what is this? So, let us just have a think. So, we call them the Routh's 5 value algebra is generally used for ATPG, that he will introduce some more symbols, and the motivation we have seen in the last slide, that 1 0 0 1. So, this means 0 1 means circuit is normal, voltage is 0, output is 0, and 1 that means circuit is at fault, some kind of fault, the answer we are getting is 1, and 1 0 means for the normal case that net or that output is 1, and 0 means because of the fault that net is appearing to be 0. But we require some special symbols to denote this, because if you do not have special symbols, then Boolean operations is not very formal. So, let us see what Roth's 5 value algebra, or this Roth has proposed some algebra having more than 2 symbols. So, what are they? Let us see. Symbol 0 and symbol 1. So, 0 means basically 0 slash 0. The normal circuit it is 0, faulty circuit is also 0. Like this is an AND gate say, and this net is stuck at 0 say. So, if you apply a 0 over here, what does it mean? In a normal case where there is no concept of any fault, then we say that this is 0. But in case of a circuit having fault, this 0 implies that normal case it is 0, faulty case also it is 0. Let us apply a 0 over here for a stuck at 1 fault say. Circuit 1 fault at the output say 0. So, what does it mean? It means that normal case the circuit is 0, the faulty case circuit is 0. Okay, that is a 0 here in ATPG implies. Now, 0 0 means the answer is 0, but if there is a stuck at 1 fault, the answer will be 1. So, we will put this as a different symbol as we will see. So, 0 0 means 0, normal case 0, fault 1 means 1 1, 1 means normal case also 1, fault case also 1. Sometimes we will use the term x. So, x means we do not know what is the value. Okay, correct. Like for example, I mean generally in a hardware, in a hard circuit, so if there is an AND gate kind of a thing say, and I power it on, I power the AND gate on, I do not put anything at the inputs, or I put some inputs which I do not know, something like this. So, we will slowly see when we will go to sequential circuits or flip flops, then we will really understand the meaning of X. X actually means that I do not know what is the value at this input or what is the value of the output. But we have to mention here very categorically that in case of circuits there is nothing called X, either it will be 0 or it will be 1. But we do not know because the circuit is not initialized properly, so that will be more clear when we will go for sequential circuit, that is the circuit is not initialized properly. So, we do not know whether the value of the circuit is at present 1 or 0, we represent it by X. Okay, that is normal case also unknown, fault case also it is unknown. But we do not know, that is, but the circuit is not having any value X when the circuit is fabricated, it is either having 0 or a 1. But as the circuit is not initialized properly, we do not know whether it is 0 or a 1 at the time of initialization. So, we say that it is X, but it is not in fact X, it is 0 or a 1 which we do not know. Okay. So, that will be more clear when we will deal with sequential circuits. Now, we come to the important paradigm called D. So, for example, we have seen the AND gate. So, that is 1 1 and the answer should be 1, but if it is stuck at 0, the answer is 0. Okay. So, we say that we represent this symbol by D. Okay. Then we say that 1 0, normal case 1, fault case 0. You take a AND gate with 0 0, the answer is 0, but a stuck at 1 fault, then the answer is a 1. So, this 0 and a 1, that is normal case 0, fault case 1, we represent it by D bar. So, basically we have introduced 3 new symbols X, so whose will be more clear when you go for sequential circuit, but for the combinational circuits D and D bar, which are the 2 important things which we have introduced. D means normal case circuit is 1, fault case circuit is 0, and D bar normal case circuit is 0, fault case it is 1. So, now we have 2 symbols, so now we can do all kind of Boolean operations and whatever you can say using these symbols D and D prime. So, that will make our things more formal. So, like if we say that 1 and a 1, say example to illustrate Roth's algebra. So, if we say that 1 and a 1, so the answer is D, because for a stuck at 0 fault, because normal case 1, fault case 0. 0 0, if the answer is 0, but if they are stuck at 1 fault, the answer is 1, we represent it by D bar. Like if the stuck at 1 fault here say, and we have a X. So, what is the X here means? X here means when the circuit is initialized or it is coming from some combination cloud, you can say, which is having some sequential elements and all, the flip flops are not properly initialized. So, we have a value which is X. It is either 0 and 1, but we do not know what is that. Okay, so, and this line is stuck at 1. So, stuck at 1 means, so had the circuit been normal, so we would have got the answer kind of a 0, because if it is 0 and a X, whatever will be, the answer is 0. But for the fault case, we know that is an X. So, basically we do not have any clear idea what is happening. So, one bit is X. So, we do not know whether the circuit is normal, because if the circuit would have been normal, we would have got the value 0. But if the circuit is having a stuck at 1 fault over here, we do not know whether it is 0 or 1. We do not know, because if X is 0, then the answer will be 0 or 0, but if the X is 1 here, so the answer will be 0 and 1 and the fault can be detected. But as we do not know the value of X, you cannot have any idea of what is happening in the circuit, so fault cannot be detected. So, basically we better write it as X, that is how we do. But if you could have written like a stuck at 0 fault over here, then we could have said the answer is 0 over here, because 0/0, because if the circuit is having a, okay, we cannot directly go for that example right now. Like for example, I was saying that if there is a stuck at 0 fault over here, then we can very easily say that the answer is 0 if there is the fault, even in the presence of an X. Okay, but here they have to apply a 1 to detect the stuck at fault, 0 fault. So, we could have said that the circuit is if the circuit is having a fault, we could have get the value of 0, but if the answer is 1 normal, then we can get a value of X, because 1 and X is X, because we do not know what is the value. Now, if X is 0, so this is 0, fault cannot be detected, but if X had been 1, then is 1 0, the fault could have been detected. So, there is no idea that if one net of an AND gate is X, we do not have any idea what is actually happening at the output of the circuit, and faults cannot be detected. So, we have to better write it as an X. So, the value of X we need not worry much about right now, because it will be more clear when you are going to deal with sequential circuits. Now, as I told you, what is the motivation of having 2 or 3 more symbols like D, D prime and X? So, because we can go for very formal Boolean manipulation, like for example 1 and a D, what is that? So, what is D? D is basically equal to normal circuit 1, fault circuit 0, right. So, now this one we AND with 1. So, what is that? This one AND with 1 means 1/1, because normal 1, fault 1. So, the answer will be 1 and a 1 and 0. So, that is equal to D again. Okay. So, this is how you get this value. So, 1 and d equal to d, 1 and d basically 1 and 1 0, because that is equal to d involves two computations, 1 and a 1 that is equal to 1 and 1 and a 0 that is equal to 0. So, actually the answer is 1 slash 0, which is nothing but d. So, basically you could have also done the same thing using the algebra like 1 slash 0 and 1, and you could have got the answer 1 slash 0, but that is not very formal, because in such type of slash, oblique, those things are not defined in any kind of a algebra. So, better we have used some symbols, like we are using say d prime. So, d prime is normal case circuit is 0, fault case circuit is 1, and we are ORing with 0. 0 means 0 slash 0, we are ORing it. So, the answer is 0 slash 0 is OR and 1. So, this is nothing but again d prime. So, it involves two computations, 0 slash 0 or 0 and 1 0 or 1, because d prime 1 0 here means 0 slash 0 and d prime means 0 slash 1. So, one computation comprises these two, another comprises these two. So, okay, so this is what is being written and you get the answer. Similarly, you can get another direct answer for not of d prime is d prime means 0 slash 1. If you invert it, you will get 1 slash 0, that is nothing but d. So, that is what they are saying. It again involves two computations, not of this and not of 1. So, you get the answer. So, what basically essentially Roth has done, so he has actually introduced two symbols. We could have also done without those symbols, but as I told you, then it does not make your algebra very formal. So, that is why the importance of this symbols d and d prime are being used. So, I mean, as I already told you that x is in logical operation, then what do you mean? So, x slash 1 is x. Basically, what do you mean by x? X means x slash x and 1 means 1 slash 1, that is nothing but x slash x, that is equal to x. So, this is how it is there. But sometimes we could have also said that x slash x and 0. So, that is equivalent to x slash x and 0 slash 0, which is nothing but 0. So, actually the answer is 0. So, anyway, we will bother more about this what you call x business in the sequential circuit, but anyway the idea I want to emphasize over here is that if you have these 5 operators in picture, so sorry 5 symbols in picture, then what is the advantage we are getting? The advantage we are getting is that we can go for a very formal way of having the Boolean function manipulations. Okay. So, now we will go for the type of ATPG algorithm, just have a look at it. So, there are 3 types. One is called the exhaustive automatic test pattern generation, that is for a given fault you have to find out all patterns which can detect it. So, how you can do that? There is no other way, but you have to apply what you call functional correctness, that we have discussed in the very initial initial phase of our testing lecture, when we have said that to test a circuit we apply, if there are n inputs we apply 2 to the power n patterns and see whether the output conforms to the specification. So, then it is very obvious that if there is a circuit with n inputs, then you apply 2 to the power n inputs to test whether everything is proper or not, then obviously for a given fault you will be able to find out which faults detect those, I mean which patterns detect which faults, and a circuit is detected if you are applying all 2 to the power n patterns, then everything is exhaustive and everything is very clear to us. Then what we can find out that if for a given fault which are the pattern it is detected, or for a given fault which are all the set of patterns which can detect it, and also the other way around. So, that is actually called exhaustive test pattern generation kind of a thing, that is for a fault you can find out which are all the patterns which are detecting it. But in fact for testing, if you remember our earlier discussion on testing, that we do not require all possible patterns for a fault. Our idea is that for structural testing with a stacked fault model, for a given stacked fault we have to apply one pattern and you have to find out that this fault is not there, because our number of samples to be tested are very high and our test time in the ATE or automatic test equipment is very less. So, we have to do as soon as possible. So, for a given fault we apply one pattern and we verify that the fault is not there and then quickly go for the other fault. So, we have to do it very quickly. So, exhaustive test pattern generation is not a very good idea, because it is difficult to go for that, and also we require only one test pattern to test the fault. Okay, then you can argue also in that idea that if you require one pattern to do that and pattern to do testing, then if you have the exhaustive test patterns for all the faults, then you can take the best one out of it. Like you can find out one pattern which is detecting the maximum number of faults, you keep that, then you take the next pattern which is detecting the next maximum number of faults and keep that, and so on. So, this can be done only if you have exhaustive test pattern generation algorithm, but again that algorithm is exponential in time and it will land up into years if you have a circuit with hundreds of inputs. So, that is why exhaustive exhaustive test pattern generation can be done by functional correctness based testing and generally is not used because of higher complexity. So, we go for basically single pattern, that is for a given fault we try to find out a single pattern which can detect it, and there can be two ways of doing it. One is called the random test pattern generation, basically that is sequential, concurrent, deductive, serial, which you have already seen in the last module. So, basically what is the idea, that we generate a random pattern and then find out how many faults can be detected by the random pattern, and then we repeat this one till all the faults are detected, or actually we have keep on, or we have completed detecting the easy to test faults. Then you have to go for something which is called sensitize, propagate and justify approach. So, there is another name for that which is actually called deterministic automatic ATPG. So, deterministic automatic test pattern generation algorithm. Why do we call it deterministic? Because we take our fault, then we sensitize, propagate and justify it, and we generate the fault. So, that is why sensitize, propagate and justify approach is called deterministic test pattern generation. So, and what is random? In random we just apply a test pattern and find it. So, deterministic test pattern generation can be two, there can be many. So, we are just going to look into two. So, one is sensitize, propagate and justify approach, which is the most widely applied approach, and we always, most of the algorithms which are using test pattern ATPG use sensitize, propagate and justify approach, which is also called path sensitization approach, and there are several others, but there is another one which is called the symbolic difference. So, quickly we will have a review of and see what introduce that what is symbolic difference based or deterministic test pattern generation, and then we will just have a look why it is not used, what is the difficulty in practical difficulty in doing it. But when you are learning about different type of automatic test pattern generation algorithm, we should just have a variety, we should just know a variety of automatic test pattern generation available in the deterministic class, because for the random class we have seen 4 like serial, concurrent, deductive and sequential, parallel, concurrent, deductive and random kind of a thing. So, 4 test pattern algorithms, 4 random test pattern generation algorithms we have seen. So, for the deterministic one, the most widely accepted is the path sensitization, which is sensitize, propagate and justify approach, but still we have to just look a variety of what is other options available. So, among that symbolic difference is one which we are going to see, but it is unlike, just like we have seen for your what you call this random test pattern generation, the most widely accepted are concurrent and deductive ones, because they can generate very quickly your random, very quickly they can analyze your circuit in one go, or sometimes if you have a highly parallel architecture, then we can go for parallel. In that manner serial fault simulations are not generally used. Similarly, in this case path sensitization is most widely used, and symbolic difference based ATPG is not that widely accepted or widely used. We will see why, just give an idea, but to know the spectrum of test algorithms we are just having a look at it. So, basically if you look by symbolic difference based testing comes from a well known Shannon's expression. So, what is Shannon's expression? If you have a function like this f of x1, x2 and x3, wherever all these x1, x2, x3 are Boolean variables, is a Boolean function, binary variables you can say, then we can write it as x1 prime, that is x1 complement in dot f of this value we have to make it 0 plus this is x1, then we have to make this as 1 and we can go for this expansion, and this can be done in a recursive manner. We all know that this is nothing but Shannon's expansion. So, Boolean symbolic difference based deterministic ATPG works on Shannon's expression. So, let us take a block diagram of a circuit. So, it has some n inputs and it has some m outputs. So, say there is a stuck at f fault at the output. So, how to do that? So, if you go for the sensitize, propagate and justify approach, that is the other. So, what we will say that if it is stuck at 0 4, then you have to apply a 1, then you have to propagate this effect. So, 0 and a 1, so it is actually d prime, normal case 0, fault case 1. If you stuck at, you apply a 1, stuck at 0. So, normal case 1, fault case it is a 0. So, it will be a d, and this effect of d has to be propagated at some output. So, once it is value of d is propagated at this output, some output, then you try to justify this one. That is actually sensitize, propagate and justify, that is your path sensitization based ATPG. Now, we will see what is the, the other which is symbolic difference, that is based on Boolean, that is based on Shannon's expansion. So, that we will see. So, same diagram we can explain both of them. So, what is that? So, let us, so first what you do, you first find out in case of symbolic difference based, you first find out the value of this net, because this is nothing but a net where the fault has occurred. You find out a value of this net in terms of this one. So, we call it g. This is a function g, these are function, because say for example, there is a lot of combinational clouds, they are the inputs, and this net is having a stuck at 0 fault which we are calling f or something like that. Then we define the function of this one without the fault, that is g of I1 to In. Obviously, because say this net is dependent on all these inputs you can say, and if some inputs are not dependent on this, then the value of this one will be x, it can be anything. But we can easily define the value of this net where this fault is there in terms of these inputs. Okay. So, that is what they are saying. Say for example, f of f in this be the function of the Boolean value of net this one in terms of all the inputs. Now, fault is not there. Now, if you want, then we know that this is actually the now we know that this is the value of g of all the primary inputs will give you the value of this specialized net g of all the primary inputs will give the value of f. Now, if you say that we can say that the value of some of these fi, what is fi? Fi actually corresponds to the ith output, then we can say right that fi is equal to g plus I1 plus I2 dot n with the function of the output lines this one at under failure at point f. So, now without the failure, so what is the function? The function is f of I1 I2 dot in with the function of the output line oi. Okay, so between 1 to n are there, so we have m outputs are there. So, we have how many functions? f1, f2, f3 dot f of m, and what are the function depends on variables I1 to in without the fault. But now, if there is a fault at the line net capital F, then you have to also introduce g. That is because now the output is affected not only by this, but is also affected by this one. So, now what you write? Now, there is a small notation we are using. So, no notation is that f of I of g, there is some notation. So, it is basically nothing, but this is the function we are having f of I. So, this is the partial derivative of this function with respect to g, that is what we are doing. So, partial derivative what we are doing is, so we know that now the output function, say some output over this one, some output say om. So, it is this function is f of m into g, because output of output om now depends on not only the primary input, but also on the fault. So, we write g, and then only we can write I1 dot in. So, this is how you can define the output m function. Okay. Now, if we say that we differentiate this one partially with respect to f of g, that is we are differentiating this output with g. So, that means we are trying to find out whether there is any difference in om with respect to the fault or not, because they are going for a differentiation. So, what we are going to write? We are going to write is this one as f of I, that is ith output with respect to g, then we write it as f of I, this one we apply a 1 and this one we apply a 0. Basically what we are doing, so this partial differentiation we are saying that, and we are doing an XOR. So, we are saying that is there any effect of this fault on this line, effect we are going to study, that is what is the partial differentiation, meaning that whether this fault is any effect on this net or not. So, when you can have an effect, if this is 1, then let us say the output is om 1, and then if the answer is 0 over here, let us say that om 0 om, this is the value of the output. Let us assume that way, that if it is 1, then the answer f is 1, that is om 1, and otherwise if it is 0 om 0. Now, to detect this fault at this net, if you do an XOR between them, then the answer should be 1, that is they should be different. In other words, if this net, or what you call, if this fault have an output, if this fault is to have an effect on this output, or for the matter any of the output, then if it is 0, whatever value say x, and if the value is 1, then the output value should be x prime, or it can be other way around also, that is x prime and x. So, that is if there is a change from 0 to 1 in this net, this output should also reflect it. If it is the case, then only the fault is detected at the output, otherwise the fault is not detected at the output. So, if the value is 0 or 1, whatever may be the case here, the output remains the same, this output remains the same, then it implies that this net has no effect, this output has no effect in the fault, and this thing cannot be used for detecting the fault. So, we write this is the partial derivation that f of I 1, that is 1 at the fault position, and all the inputs XOR this one should be, basically this is what is the partial differentiation, and if you want to detect the fault at that net, then the answer should be 1. So, now let us say this, so this is the definition of the partial derivative, that means it is trying to find out whether there is any difference, or whether any difference at the output I for this fault at net g, that is it is want to find out if there is any voltage change at net g, whether there is any effect at the output of net, at the output of net I, output I, that is what is the definition. Now, for detecting a stuck at 0 fault at f, what we have to do? Obviously, we have to apply, we are going to detect a stuck at 0 fault here. So, what we have to do? We are going to stuck at 0 fault here. So, we have to apply a 1 over here. So, what we have to do is very simple. So, first thing is that apply a 1. So, how do you apply a 1? So, g of I1 dot In should be equal to 1, because these inputs only control this. So, we write something like this, g of f of I1 to In equal to 1, this is the first condition that has to be satisfied. And then what you have to satisfy? Then you have to satisfy that at least one output, at least one output should be there where this, because 1 we have applied and this fault is 0. So, 1 0, that is equal to D, now we have got a D. So, there should be at least one output where this D value is propagated, can be propagated, or in other words there should be at least one output where this effect is propagated. So, how do you know that the effect is propagated? We have to find out that any net, any output should be sensitable, what you call can be sensitized or is sensitive to this change. And how do you know this change? So, we have to write this one as f of j. There actually they are saying that there exists at least one j between I to m, that is at least one j from between 1 to m, that is at least one output where this it is sensitized, where the output is sensitized if you put a 1 over there and a stacked fault is there. So, if you put a 1, that means it is the normal case, and this is the output at the output at OJ, okay, if there is the stacked 0 fault, and this is the normal case, because output is now dependent on the primary inputs as well as the value at f. So, value of f is stacked 0 means this is the fault case, the output value is 1, that means it is the normal case. Okay. Now, you have to, we are saying that is the partial differentiation of Fi with the fault. So, it is saying that there exists at least one output where if the fault, that is at least there is at least one output for which the fault effect is sensitizable, that is f of j, that is for jth output, if you apply a 1 in the fault location and all the primary inputs, XORed with if you have a 0 at that fault location and you apply this some primary input, the answer is 1. That means, the output j is different with fault compared to normal. Okay, so, it says that if this is the case, then the fault is detected. Now, what is the test pattern? All the variables that is satisfying these equations are the test pattern. So, you are going to get a exhaustive test pattern for this range, and in fact, that is what I told you, that exhaustive test pattern, this is nothing but the complexity of this algorithm is 2 to the power n, and it is something equivalent to all fully functional testing using 2 to the power n type of inputs and finding out whether there is a difference. So, that is why, because of this high complexity of Boolean is not a very efficient for large circuits. So, therefore, we do not go. Now, let us just see what they are saying for the stacked 1 fault. So, if there is a stacked 1 fault you have to detect at f, then what you have to do, this is stacked 1 fault, then you have to apply a 0. So, f of this function is actually f of f, say, that is g, what you call. So, in this case you have to apply a 0. So, by controlling the primary inputs in such a way, so that this g, that is the fault location, should have the value 0. Now, again, what is the next case? The next case is that there should be at least one output j between I and m such that it is sensible to this effect, that is the stacked 1 you apply a 0, normal case 0, fault case 1, stacked 1 we are applying a 0, which is nothing but d prime. So, this d prime effect should be available at least some output f j. And how do you represent this? So, stacked 1, so this represents fault, and 1 this represents normal, and this value should be different at the output. Why? Because this g is 1 here and this g is 0 over here, and these controls, these are the primary inputs. So, now which variables will satisfy the equation, or which combination of variables will satisfy the equation? All variables, all combinations of I1 to In which actually satisfy this equation and this equation will be a test pattern for that stacked 1 fault. Now, again, I mean the exhaustive number of test patterns can, what you can call, satisfy these equations. So, this is actually a very high complex algorithm, and therefore, we do not need, even if it can do satisfy automatic test pattern generation algorithm by what you call a deterministic approach, but still you do not take it because it is more or less equivalent to functional testing, which is exponential order complexity. So, now we will go for the approach which is widely used for test pattern generation, which is called path sensitization based ATPG, or which we are continuously calling as path sensitize, propagate and justify. So, what do you mean by path sensitization? Already I told you that if there is a stacked fault, we have to drive it to the opposite value. This is just like there is an electric bulb, then you have put it is fuse. So, you have to make it, you have to give power on, so that it goes to value 1, that is it tries to glow. Okay, and then if the bulb is, if for example say that the bulb cannot be switched off, it is always on, then what you have to do, you have to try to switch off the bulb, then the bulb if it continues glowing, then you can know that basically it is a stacked 1 fault, or the bulb is always on kind of a fault. So, to detect a fault you have to always sensitize, that is you have to give the reverse value of the fault. Now, then is called the fault propagation, that is the fault effect has to be set to primary output, because in case of testing we know that we can only control the primary inputs and observe the primary output, intermediate lines we cannot control. So, the effect has to be gone to some primary output where it can be observed, right. And this line justification means, because all these steps we are doing manually, I mean all these steps we have done require some kind of, I mean all these steps like fault sensitization and fault propagation, all these things has to be controlled by the primary inputs. So, now you have to justify that this sensitization and propagation can be done by appropriately setting the primary input lines, because we cannot control the internal nets. In this, the signals at the internal nets or some primary inputs which which assigned for fault propagation are justified by setting the primary inputs of the line. That is what is being said. So, what we say? We say that in this step the signals at the internal nets or primary outputs which were assigned in these two steps. Like for fault sensitization, what was the assignment? The assignment was if it is stuck at 0 fault we apply a 1, and if it is stuck at 1 fault we apply a 0. So, that internal nets we set some voltage. Like fault propagation, that means we set some primary input, some internal lines, so that the output effect or the fault effect is propagated to the output. So, we set some signals values in this circuit in some way, and fault line justification will say that yes, that can be done by appropriately setting the primary input. So, we will see with an example. So, that it is how is it possible. So, what do you mean by that? So, that is actually called line justification. So, once it can be justified, then you are very happy, because sensitize, propagate and justify has been done, your fault value has been propagated to the output, fault effect has been propagated to the output, and you can observe it. But we are always saying that this is straightforward, false sensitize, propagate, justify, false sensitize, propagate, justify, but life is not very simple, because always or many times you can have conflict. That is a conflict, that you have gone for false sensitize, you have gone for fault propagation, but there is no primary input combination which can satisfy false sensitization and propagation. Then you have to go for alternate path, and so that we will see by an example. So, that is why it is a very difficult thing. So, like what we have emphasized is that in case of right now we are just going back a few slides or a previous lecture, what we say that in random test pattern generation our answers are very simple. We propagate the circuit we traverse the circuit in one direction and we get the result in case of deductive or concurrent, that in one full scan of the circuit we can find out this pattern detects how many faults. Similarly, if we say that sensitize, propagate and justify can find out your faults, that is once you sensitize, you propagate and justify, then that is also one scan of the circuit. Then why do you are going for random test pattern generation? So, one advantage of random test pattern is that we have seen that they say that in one pattern you can detect multiple faults that can be detectable by the pattern. But at the same time it is also said that this random test pattern requires one scan of the circuit. So, similarly, we can also question that sensitize, propagate and justify also does one scan of the circuit. You sensitize, you propagate and you justify, but life is not very simple. Many times we have to go for iteration, that is you sensitize the fault, propagate its value at the output, then you find out that this cannot be justified, that there are no primary input combinations which can justify sensitize and propagate step. So, again you have to find out some other paths or alternative mechanisms to do that. But this problem of backtrack is not there in random test pattern generation. So, we now see an example, then things will be more clear that what do you mean by backtracking. So, had backtracking not been there, then always we could have totally thrown away this random test pattern generation and we could have gone for the path sensitization or sensitize, propagate and justify based approach, at least from the complexity point of view. So, let us see. So, let us consider this circuit as an example. So, let us take that there is a stuck at 0 fault at this one. So, if there is a stuck at 0 fault, so we have to apply a 1. So, we say that we apply a 1 over here. So, apply a 1 over here. So, normal case 1, fault case 0, that is actually nothing but D. So, now we are going by the Ross algebra. So, we have to write, we do not write 1/0, we write basically D. Now, the value, now this is sensitized 1 and fault 0 I have put a 1. Now, you have to find out a path through which this value can be propagated to the output. So, you can see this is one path, okay, and there is also another path through this one. So, you can take any one path, or sometimes also you can try both the path together. So, let us for the time being first try with this path. So, what is the path? Path is E, F, G and H, this is the path, okay. So, now let us try to see the path. So, that is now sensitization, now we have to propagate it. So, the value of D we are going to get here, AND gate. So, this is not a non-inverting gate, this the value will be there. So, this again we are propagating this path, this OR gate and NAND gate are non-inverting gate. So, D will be propagated. Now, you can see that this is an inverting gate NAND gate. So, the value will be D prime over here. So, anyway both D and D prime can detect the faults, because D means normal case 1, fault case 0, D prime means normal case 0, fault case 1. So, both of them can detect the faults. So, now is the D prime. So, we are happy with it. So, this is called the fault propagation. Now, sensitization is done, fault propagation is done. Now, we have to justify that this setting of the lines, that is this propagation and this sensitization is possible. So, in this case the sensitization is very easy, it is possible just by setting B equal to 1 because the primary input false. So, you can easily do that. That means what sensitization is done. Now, we have to see that whether propagation is possible through the primary inputs. Okay, so, this is D prime. So, you have to obviously put a 1 over here, because if you put a 0 over here, then the NAND gate output is 0, then all the problems, all the whatever effort you are doing is lost. So, you put a 0 over here. Now, this is 0, this is OR gate. So, obviously, you have to put a 0 in case of a NAND gate, because if the OR gate input is 1, then the output will be 1 and our effort is lost, right. So, now you put a 0 over here. Now, if you want to put a 0 at the output of the AND gate, then what you have to do? So, if you want to get the output of the NAND gate as a 0, so this is actually 1. So, if you want to get the output of NAND gate 0, then you should have one input as 1 and this input as 1, correct. And what do you call, and this gate is D, this is D, so A equal to 1. But now you see, then we have got a big conflict over here. To get the answer as 0 over here, we need a 1 over here as well as 1 over here. But this net is basically D because of the fault, and this net is D. So, we require a 1, but actually D is being applied. So, this actually leads to a conflict and we have to try for an alternative path. So, that is why I told you that although we are telling from the first lecture onwards that sensitize, propagate and justify, sensitize, propagate and justify is a very good algorithm, because for difficult to test faults you can find out the patterns, but life is not very simple, because sensitize, propagate, justify, there is something called failure. Sensitize, propagate, justify, failure, iterate. Sensitize, propagate, justify, failure, iterate. You have to keep on doing it till we get an answer, or sometimes the fault, we may land up and saying that the fault is non-testable. Okay. So, this is one option is gone. Now, what is the next option? The next option is we have to try this another alternative path that we can try from this one, correct. So, let us see the alternative path. Now, D is there, this is an inverting gate. So, you get a inverting over here. Now, this is the path, because these are in propagation path, sensitize already is done, that was successful. So, now again D prime, because this is a non-inverting gate. This is a non-inverting gate, correct. So, this is a non-inverting gate. So, again D prime, now this is an inverting gate. So, you get the value of T over here. Now, let us see how can we justify this. So, in this case you have to propagate the value of this one to this one. So, this is D to D prime, so D prime to D, because the inverting gate. So, you put the value of 1 because this is the controlling value, so non-controlling value for a NAND gate. Now, you can see this D prime has to be propagated over here, so OR gate. So, you have to get the value of 0 over here, correct, and this is also a D that you have to know, because this is a D, because stuck at 0 and 1, but to get the output 0 at the AND gate you put a equal to 0. So, you are done. So, now this path sensitize, propagate and justify, everything is satisfied. So, let us see what we have satisfied right now. So, sensitization you stuck at 0 1, so you apply a 1, so that is fantastic, sensitization is successful. Now, you have to propagate the value through this output. So, you have propagated this one. Now, we get a 0, sorry, we need a 1 over here. Now, OR gate, so something is propagated, so you get a 0 over here, you need to apply a 0 over here, because this is non-controlling input for OR gate. And for AND gate, if you want to take the output as 0, you apply a 0. So, the pattern A equal to 0, B equal to 1, C equal to 1 and D equal to 1 is the test pattern to detect the fault. So, what is the test pattern? A equal to 0, B equal to 1, C equal to 1 and D equal to 1, and output is D, that is normal case 1, failure case 0. This is the test pattern which detects a stuck at 0 fault ever. So, we have found out a test pattern to detect this fault, but we have to remember here that it has come with a cost of iteration. So, sometimes there can be multiple iterations that you can fail in both the paths, then you have to try to propagate the effect to both the paths together, and we may have to try keep on doing it till we are exhausted and we found that there is no more alternative paths to do it, then you have to declare that the fault is a non-testable fault. So, you can understand that to detect a stuck at 1 fault or stuck at 0 fault by sensitize, propagate and justify approach, so many times you may have to iterate through the algorithm, because you may have sensitize, propagate, justify, failure, sensitize, propagate, justify, failure, and keep on trying alternative path. That is why we always go for sensitize, propagate and justify approach only when we fail by random test pattern generation, because in random test pattern generation sometimes we may not detect some faults and we have to stop. I mean, we have to retry those faults, but this is not a direct clear concept of iteration. That is, we apply a random pattern, some easy to test faults are detected, some are not detected, we take them for the next round and keep on doing it. So, in a broader sense, in sensitize random test pattern generation, there is no concept of iteration, as in bold quote unquote, which is there in sensitized propagator and justify approach. Therefore, only for difficult faults we try this approach. Now, let us go for a question answer session. So, we have a fault over here, that is the stuck at fault over here. Now, this is circuit. Now, we try to generate a test pattern for that using sensitized propagator and justify approach. So, obviously stuck at 0. So, you apply a 1, correct. So, correct, you apply a 1. So, normal case 1, you can get the fault case to be a 0 over here, right. So, in this case normal value is 1, fault value is 0. So, actually sorry, the answer is not a D prime, it is D, okay, because you have the sensitization you have to do, you apply a 1, then 1 and the normal case fault case is 0. So, it is a D over here, sorry for the typo, it is D. So, now it is a non-inverting gate, so you also get the answer as this one, correct. So, you stuck at 0, you apply a 1, this is the value. So, this is nothing but D, and then it is a non-inverting gate. So, you get the answer as D over here. So, this is the propagation path, because there is only one propagating path in this case, there is no other fan out here. So, there is only one path where you can propagate the value. So, that is what we have done, D and D over here. Now, let us see what happens. So, I am sorry, let us again redraw, it is 1 D, answer is D. So, it is an OR gate, we know that we have to get a value of 0, correct. So, this is the value of 0 over here, because you have to, now we are sensitized and stuck at 0, you apply a 1, this is sensitization, that is D. Now, value is propagated to here, and we are justifying it. Whether this path is possible through what you can call the primary, a combination of primary. So, it is 0. So, it is very correct that you have to apply a 0 over here for OR gate. So, getting a 0 over here implies that B is equal to 0. So, B is equal to 0 implies that this is a 0 over here. So, we land into a conflict, but to state a stuck at 0 fault we require a 1 over here, but again to propagate it we require a 0 over here, and it is again a 0 over here. So, this is a conflict. So, now you can see that this is a big problem over here, because there is no other alternate path for the circuit. So, this fault is an untestable fault. So, sometimes it may happen that in this case there is only one fan out. So, we have in one iteration we stopped and found out that the fault cannot be detected, but for a general case it may happen that there is a large number of alternative paths, and for none of them the answer is successful. So, you always have to go for sensitized propagate justify failure, sensitized propagate justify failure. We keep on doing it for some 100th option possible, and then we find out that the fault is non detectable, and our algorithm has taken a lot of time and we are in a bad situation. Now, let us just analyze for very quickly why this fault is not detectable. So, faults are not detectable only if there is some redundancy in this circuit. Like in this case, what is the function? This function is A dot B at this point, and it is, and this one is actually A dot B, this A dot B and this OR plus B. So, this is nothing but B into A plus 1 kind of a thing. So, this is nothing but B, correct. A plus 1 is 0. So, this net is nothing but actually a straight line called B. So, this circuit has lot of redundancy. So, if you actually optimize this circuit, you will find that A is equal to nothing but B. So, that is nothing but this is your circuit. So, because of this, if there is some redundancy in this circuit, and fault those lines cannot be detected. But sometimes we do have to have redundancy in the circuit to match clock skews and several other design paradigms. So, all those redundant parts, if there is a fault, those faults cannot be detected. But our ATPG algorithm, if like sensitized and basically they are the culprits. Those what do you call those redundant parts are actually the black nightmares for the testing people or the test engineers, because if there is a redundancy in the circuit, neither random test pattern can detect those faults. So, they will be classified as difficult to test pattern, like we have seen in the squab algorithm, that because of some redundancy in the circuit, that the squab value was 6, but actually it should be infinity, because that fault cannot be tested. So, anyway squab will classify them as a difficult to test fault, because squab will never give the value infinity kind of a thing, because of the heuristic, or what you call because of some redundancy, or because some simplicity you have kept in the algorithm to make it a quick algorithm, so that you get the answer fast. So, squab will give a very high value, but you will never say infinity. So, it is a difficult to test fault, and if you keep on trying sensitize, propagate and justify approach, every time you will be failing. So, in this case, this example circuit, there was only one fan out path. So, you have just tried in one go and you have failed, and you have not, and you did not go for iteration because there was no other option. But for a general circuit there can be lot of options, but all the options are definitely bound to fail. Now, why they are bound to fail? Because they are redundant circuits and those faults cannot be tested. So, you will keep on doing sensitize, propagate and justify and keep on failing, and in the end what you are going to do is that you are going to declare that the fault is not testable, but by that time you have taken lot of your computation time. So, that is not a very good approach of doing it. So, now, this comes to end of the basics of ATPG and ATPG algebra and how we can generate test patterns using sensitize, propagate and justify approach. In the next lecture, we are going to take ATPG, that is actually the sensitize, propagate and justify approach by a very well known algorithm which is called the D algorithm. So, we will see formally how D algorithm is used to go for sensitize, propagate and justify approach based test pattern generation. So, that we will be looking up into the next lecture. Thank you.